This is not particularly sturdy. All right. Hi, everybody. So this talk is more about just Scala as an ecosystem. Crap. OK, this is more of a talk about Scala as an ecosystem for machine learning in general, sort of a survey, an overview, not so much the details of any particular algorithm like LDA. But I guess I'm just, the main point that I'm trying to make is that even though Scala may not quite have the same ecosystem that Python or R have, it's definitely a good enough start, and it's definitely much more production ready, and especially when executing at scale. So first I'm going to overview what we might or might not be missing from R and Python, what the JVM alternatives are, and hopefully Scala alternatives, so as not to have to write boilerplate Java code. And actually, I'm going to show how to develop a really simple sort of toy example algorithm from scratch in just a few minutes. So first of all, obviously, machine learning is ubiquitous. It's everywhere from fraud detection and spam filtering to speech recognition, OCR, and even self-driving cars. But in order to support so many algorithms, you actually have to have tons of models. And these are just a few regression models. They're actually probably, at least an order of magnitude more algorithms for regression itself. A bunch of classification algorithms. Again, the list is way, way longer than this. Same with clustering. Oftentimes you may need something less vanilla than, say, k-means. For example, you could do clustering using self-organizing maps, which is a neural network algorithm. Essentially, you need a variety of algorithms to solve a variety of problems. And in that case, you would rather have a bunch of libraries so that you don't have to write all of them from scratch, because some of these algorithms are quite complex and quite tedious to implement, and especially to implement efficiently and implement efficiently at scale. So in the case of the R ecosystem, you've had this exponential explosion of the number of libraries. There are over 5,000 libraries in R right now, which cover everything from the design of experiments and traditional statistics to machine learning, NLP, obviously plotting, and a lot of other areas. Python obviously is quite rich in that respect as well, from linear algebra and NumPy to plotting in MLLib, machine learning in scikit-learn, even symbolic computing in SymPy, which is something that only Octave and MATLAB offer other than Python. But you also have some really advanced solutions that are unmatched in other languages, such as Theano and PyBrain for deep learning. And so this ecosystem is quite rich as well. I mean, the testament to this is the fact that you can write a digit recognition algorithm in Python in 30 lines of code. And in fact, out of that, we only have one line to train the support vector machine classifier and one to predict. And the rest is just visualizing the output on the console. And that just shows you how powerful these things are. So essentially, this is the kind of level of support that we're aiming for in Scala. And it's not quite there, but at the same time, as good as Python and R are in terms of the number of libraries, obviously they have a lot of problems, and my least favorite issue about these languages is that they're stringly typed. So I can just have a typo in the code, let alone a type error, and have it fail at runtime after a few hours simulation because that particular path has not been executed before, and that is really painful. And the runtimes themselves are quite terrible as well. Like everything is by copy in R, so you waste a lot of memory. The garbage collector is really slow. Python has the global interpreter log, so you program as if you essentially had to scale through multiprocessing on a multi-core machine, like it's, I don't know, CGI web programming in 1995. Sorry, did you have a question?
Yeah, I have two comments. Comment back to the Python library slide. You showed pandas.
Oh, I think I mentioned. Did I not mention pandas? Oh, I did mention pandas. Yeah, that's data frames for Python. Yeah.
Sure, and then a comment on that slide. And so everything in our body is by copy, unless you do the really funky thing, like making assignments in the kernel environment.
Right, that is a good point. That is a good point. R has some workarounds. R actually has some really clever tricks to do a lot of really weird things. Like, for example, you can inspect the previous stack frame and figure out what the variable names were that were passed to this particular stack frame and stuff like that. So they do have a lot of crazy things that you can do. You have actually full control over the interpreter.
It's pretty nasty because you need to know the name of the object in the environment.
Right. So it is nasty, and you know, the way obviously people scale R and Python is that they write everything in C++ or Fortran and then have a wrapper around it, right, in order to scale. But that's not quite nice. You have to use two languages, and it's a pain. But you know, the other thing is, of course, that these languages encourage imperative programming, and math is declarative. You know, and I'm not just talking about piano numbers, but I'm talking about the fact that, for example, the output of the last layer in a neural network is dependent on its input, and the input is dependent on the output of the previous layer. So you can essentially write everything as one big recursion. So you know, it's more than just like stylized examples like Fibonacci numbers. Everything could be potentially recursive quite elegantly, and you know, no side effects in math, obviously. You know, people say that R is actually a pretty functional language because you can have a function declared within a function, and you can pass lambdas and stuff like that. But you know, if you don't have tail recursion, then obviously you cannot write much using the functional paradigm in R. In Scala, you obviously can. So, you know, how does the ecosystem compare? Because sure, we're purists here, or semi-purists at least, and we believe in FP and we believe in static typing and so on. And the JVM is probably a better runtime, but you know, if you don't have any ecosystem, then you know, people are not gonna give you all the time in the world to write the libraries because you have to deliver results, right? It doesn't matter what the runtime is at that point. So I just want to make the point that the Scala ecosystem is actually not that small. So for example, for numeric abstractions, you have Axel and Spire. Spire is really phenomenal. These guys have come up with really crazy things such as a floating point filter to have the accuracy of essentially a big decimal, and while keeping the performance of a double. I mean, I don't even know how they come up with these things, but it's really cool. And a lot of nice category theory and stuff like that as well. If anybody knows the difference between a rig and an RNG and a ring, then bonus points for them. Okay, but from a more practical side here, sort of a higher level of abstraction, linear algebra is the bread and butter of machine learning, and it would be a shame if we didn't have good libraries. So the three libraries at the bottom are actually Java-based, but their APIs are not that bad. ND4J has nice backends. It runs, you know, on CUDA and BLAS and all kinds of other backends, but unfortunately it still has a mostly Java API. There's ND4S now for Scala, which is a major improvement. Breeze, which is the first logo by David Hall. This is part of Scala NLP, and it's a really phenomenal linear algebra library that I use all the time. So there are lots of options. And obviously the notebooks, and Andy is here. So this is my favorite of the notebooks, but I listed all four. And they're plotting solutions. The notebooks obviously have plotting solutions on their own, but there is also Wisp. For web-based plotting, there's the Lightning visualization server, which is language independent. It has a REST API. You can use it with anything. But even Breeze has visualizations, although those are based on J-free charts, so not as nice. But Breeze's focuses on linear algebra, not so much on visualization. And with respect to machine learning, you know, you have a lot of machine learning in Breeze. There's also stuff in FACTORIE. There's MLLib, of course, and the H2O fork of Spark as well, and deep learning for J for deep learning. You know, these are somewhat deficient. The other solutions, you know, that I just mentioned for basic sort of vanilla machine learning, but where the JVM really shines is NLP. And at the bottom, we have the three Java-based libraries, including Stanford Core NLP. But the three ones at the top are all purely Scala-based. So we have FACTORIE, POC, and Epic. And POC actually does parsing on the GPU, so it's really fast. So you can have performance and elegance at the same time. But what if there is no library for something, right? I would like to make the claim that it's really easy to build it in Scala just because it's a good language. So, obviously we have functions as first-class citizens and functors, monads, and, the whole category theory shebang. And, not going deeply into category theory, I would just make a more basic point, such as, referential transparency matters, and immutability matters as well, and just the fact that I can do declarative programming and not get a Stack Overflow. But also Scala has implicits, and this was the point that Malcolm was making about type classes. It's really nice to be able to write one algorithm that will run on Flink, Scala collections, Spark RDDs, et cetera, et cetera. And of course, you can write nice DSLs because the language is very expressive. And just the fact that you can have you have type inference, so you don't have to write a lot of boilerplate with regard to the types, and you don't have to write the builder pattern because you have named arguments to your constructor, for example. That's pretty nice. So just the language is really neat. So just in a few minutes, actually less than 15 minutes, I'm going to show you how you can create two optimizers, stochastic gradient descent and autograd, using Breeze's linear algebra, develop linear regression from scratch by implementing the cost and gradient functions, have the implicit conversions in place so that you can do the computations over Scala collections and Spark RDDs, plot the results, and run against a synthetic data set. And actually, I wanted to make a special point about this abstraction over Scala collections and Spark RDDs is that the point here is that, sure, you can make a conversion to an RDD by parallelizing the Scala collection using the Spark context. But the problem is that if you're running on a single machine and you don't have much data, Spark will actually slow you down because it's doing scheduling and stuff like that. And if your data is small, you might as well run faster using Scala collections. And this is the point that Databricks was making, that Project Tungsten isn't just about code gen and native memory use and stuff like that, but it's also, there was a plan in the next couple of releases to basically have local versions of the libraries that would run without the overhead of Spark itself. But it's really not that hard if you have the kind of type class that Malcolm was talking about. So linear regression, before we go into the code, you have a feature on the x-axis, and you have a target on the y-axis, and you're trying to predict y as a function of x. Obviously, this relationship is not perfect. Therefore, we're trying to minimize the sum of squared residuals. And we could have many more features than just one, but in that case, we wouldn't be able to visualize this. So this is a really simple model, and the linear algebra is really straightforward. You just have your beta matrix, beta vector, which has the coefficients for the features, and your X matrix, where each row is an example, and each column is a feature for that particular example. So that should be pretty straightforward to implement. Now, with regard to optimizers, there's stochastic gradient descent and autograd here. Normally, stochastic gradient descent is just represented as performing the computation on a mini batch or even on a single example in case of online learning. And in that case, you calculate the gradient for that particular example or the mini batch and subtract the learning rate times the gradient. However, stochastic gradient descent converges poorly unless we're actually doing learning rate annealing, which is what I'm mentioning here. In the case of autograd, instead of annealing by the number of iterations and the number of examples per mini batch, we're doing that based on the norm of the gradient history for each dimension. So the bigger the gradients in a particular dimension, the less you learn in the future. So it's kind of like the authors of autograd essentially summarize that as TF-IDF, but for optimization. You have the cost function, which is really simple, sum of squared residuals, and the gradient is really straightforward as well if we just take the derivative. So to actually implement this really quickly, I'm just going to skip the step with the type classes because Malcolm already covered that, but I'm using the same thing because we're doing this as part of the book that we're writing together about machine learning for Spark. So he already did a very good demonstration, so I'm going to skip that. But let's just look at a couple of other things. First of all, the optimizer is going to simply take some hyperparameters here, such as the number of iterations and the initial learning rate and the momentum. Momentum is a way to preserve the direction in which you moved in the previous iteration. That reduces the variation in the direction in which the movement is unstable, and boosts it in the direction in which the gradient is small but the direction is stable over the last few iterations. And for the update function, this is actually where we provide the weight update. So since Scala is functional and and functions are first-class citizens, we can basically provide a function object here which defines our particular update rule, which is different between ADA grad, ADA delta, SGD, VSGD, and all of the other optimization algorithms. And all we do here essentially is executing the cost function, which we already defined for linear regression, at least mathematically, and then we get the optimization history value, and then we call the update function a bunch of times, and we don't even have to write a for loop because we could just do a fold. So since it's Scala, and now we actually need the optimization algorithms, because this is actually the key issue, right? We need to know how to update the weights. So this is all of stochastic gradient descent, which will actually run on both Spark and Scala collections. ADA grad is a little bit longer because it has this step where you scale by the diagonal of the Hessian, which is basically the accumulated gradients on the diagonal. And so it's a little bit longer, but again, very little code, right? You need to do some sampling, and this is important because we're doing mini batches, and if we were to do full batch gradient descent, it would be extremely slow. With mini batches, it's much faster. However, it's still faster to do mini batches than to do pure online learning because we're using vectorization. And actually, this is an important point, right? The JVM is really horrible at optimizing numerics because, first of all, for a lot of data types other than arrays of primitives, we have boxing, and then you lose a lot on object construction and destruction, and on basically dereferencing these references instead of having cache locality and so on and so forth. But also, the JVM is really bad at vectorization. Vectorization was introduced in Java 7, update 40 or something like that, so fairly recently, and it only works on basic Java 4 and while loops. But if you have anything more complex, it's not going to work, and it doesn't even support recent vectorization SIMD features of CPUs such as AVX on Intel or Neon on ARM processors and so on. And this actually makes a big difference because if you're running on floats, you can run on 8 floats at a time instead of 1 float with SSE2, I believe, and on 2 doubles instead of 1 double. So you can get major performance improvements. So basically, in this case, because Breeze, the creator of Breeze, David Hall, took the time to integrate this with BLAS, you're actually running linear algebra in Fortran, even though you're writing Scala code, which is really awesome for performance reasons. Let's see, what else? I did some plotting here. This is actually the only side effecting code because plotting is side effecting. This is using Wisp to do plotting on the web. Wisp comes with an unfiltered web server, so you don't even have to start your web server here, which is pretty neat. And for linear regression specifically, you have to implement the gradients and the cost function. So the cost function is trivial, sum of squared residuals. The gradient is equally simple. And since this is Breeze, we can do really nice computations. So dot T is transpose of the matrix, and And we can just use operator overloading here. Colon plus is the element-wise addition of two vectors. So again, the fact that Scala supports overloading in this particular case is really useful because you can infix and you can use actual mathematical notation. And let me just do a quick demo here. So I generated this fake data set which has a Gaussian, a bunch of Gaussian random numbers for the feature, and then the target is the intercept of 3 plus 10 times the Gaussian from the feature plus another piece of Gaussian noise at the end. And as you can see, the expected coefficients were 3 and 10. For SGD, I got 3.4 and 9.2 because SGD tends to converge very slowly, even with momentum. Adagrad converged much faster, and in fact, it got the right result already. But the interesting thing, for example, is that Adagrad was extremely unstable at the beginning, while SGD had very small errors. But as time went by, Adagrad actually won. And this is actually why I really like plotting stuff, because if I look at 10,000 iterations and I have to look at all these numbers, I don't really know what's going on. But here I can actually see this. And this is another reason to use notebooks as well, which have very good plotting. And that's basically it. So linear regression may be a really trivial algorithm, but what if you wanted to implement, say, LDA like Alex, or I don't know, support vector machines, or let's say long short-term memory neural networks, right? As long as you can distribute the optimizer and then collect the partial results from the stochastic computation, get your partial gradients and be able to do the updates, it should be simple to distribute really any algorithm that is amenable to distribution. Obviously, not every algorithm is amenable to distribution. You cannot really distribute linear programming, and SVMs are actually really hard to scale, by the way. So there's an implementation in MLLib, but it's not. But SVMs in general are not very scalable. But tons of algorithms are, and since you can have this nice indirection of a type class between Scala collections and RDDs, and even Flink data sets, you should just write your code once and be able to scale it, as long as your computation can be made stochastic. So that's it. I guess the key thing is, the Python ecosystem didn't have the libraries that they do right now a few years ago, when the R ecosystem was essentially complete. And people just hated using R and SAS and other technologies, and they actually got busy to build stuff. My claim is that Scala may not be Python, and you may not have Theano and PyBrain and pandas and all of these things, but we're not starting from scratch either. There's already a really nice ecosystem. We just need to keep building stuff. So I guess let me just bring up the slides for a second. So this code is on GitHub, and this is actually part of the book that I'm writing with Malcolm. So the bigger code, which will cover other algorithms that we mention in the book, are in the second repo. And we don't really have a date from Manning when the MEP is going to come out, but I assume it's really soon, since we have half the book written. So hopefully the publisher will get busy soon and do their part. But we're covering stuff such as how to do a good online variance calculation, and how to do naive Bayes at scale, and SVMs and locality sensitive hashing and stuff like that. So essentially the usual vanilla, popular machine learning. But the point of the book is not to show you just recipes. It's how you distribute those kinds of computations. So if you get stuck and you have to implement an algorithm that's not covered, we're trying to promote the mindset of how to solve these problems, not just provide a recipe book. So that's sort of the intention. And I guess that's it. Questions?
As it compared to the Spark using Python?
Sorry?
As it compared to the Spark using Python?
Spark using Python? Well, first of all, here's the problem with Spark using Python, right? PySpark exists, of course, and you can use pandas, and you can use, everything from PySpark. The problem is that you still have to distribute your algorithms. My current understanding of PySpark is that the algorithm coverage in PySpark is much less than in regular MLLib, and this is because these bindings have to be written. So you don't have to rewrite the algorithm in Python to run MLLib, but you have to do the Java bindings to the Python code base in order to expose those APIs for the Python user. So the Python coverage of algorithms is actually behind the Java and Scala coverage. Besides, there's more to the machine learning ecosystem on the JVM than just that, because as much as I used to poo-poo, Apache Mahout a few years ago, now they have a really nice Scala DSL for linear algebra, and they're adding, all of the algorithms they're adding right now are based on Spark, and they're actually trying to achieve parity with Flink as well. So there's quite a bit of work there at the moment. So it's not the same Mahout that I remember from, say, a year or 2 years ago. And so I think building stuff in Python is relatively straightforward because you have a nice ecosystem already. But if you have to distribute your computation by using, for example, NumPy, then you might as well distribute it using Breeze and Scala instead, since you have to make an effort to actually distribute the computation to begin with. The same problem is the case with Spark R, although I think the Spark R parity with Scala is going to be a little bit faster. They've kind of accelerated this effort. But again, it's parity, it's not an advantage. So, yeah.
So you mentioned that there is no symbolic toolbox for Scala. What would be the use of it, and how urgent is that?
Well, that is actually quite urgent. Yeah, what would be why would it be important to have a symbolic toolbox for Scala? And yeah, basically, why would that be important, right? So, well, first of all, I'm not talking about this kind of uses that we know from Mathematica or Maple, where we, provide a huge equation and want to just simplify it or solve a differential equation or whatever. There are many other use cases. For example, Theano for deep learning has this feature of automatic differentiation, and you can basically say, oh, I just dreamed up a crazy architecture where one layer is going to be convolutional, another layer is going to be traditional perceptron layer, another layer is going to be subsampling, another is going to be upsampling, another is going to be an inverse convolution. As long as you know that that each particular layer, how to construct any particular layer, Theano will figure out how to combine them and how to apply the chain rule in any abstract way for all the architectures that exist. So you can compose a new neural network that never existed, and it's just going to do it. And that is actually a big advantage. There are many others, but this is actually the one that's closest to my interest. I haven't done like traditional symbolic computing MATLAB style or Mathematica style in a while, but this is actually quite useful for certain problems. Yep?
There are at least two libraries important to note in Scala. There is Figaro for progressive programming, which is very important in my opinion, and the other is Oscar for constant programming language, for optimization, operational research, and so on, so you can add that to the mix.
Cool. That's really good news. Yeah. So there are two libraries for symbolic computing. One was Oscar, and one was what? Figaro. Yeah. Yeah, I actually heard about Figaro. I never used it really. There were also some really well-known Java libraries for quite a while, although my understanding is that those particular libraries have a commercial license, even though like academic use is free. But the Scala ones, the Figaro is definitely like Apache or something, right? Or MIT, yeah. So that's actually really good news. I'm going to check it out for sure. Thank you. Any other questions or ideas? All right. All right, thanks, guys.